In a lab at Los Alamos National Laboratory, there's a single qubit sitting inside a dilution refrigerator, cooled down to a fraction of a degree above absolute zero. And every few microseconds, someone is watching it. Not with a microscope, obviously, because you can't actually look at a qubit the way you'd look at a rock or a cell under glass, but with a continuous stream of measurements, little electronic pings that ask the system over and over again, what state are you in right now? And normally that stream of measurements just tells you what's happening, sort of like checking in on a pot of water to see if it's boiling. But in this experiment, the physicists weren't just watching, they were using what they saw instantly to reach back in and reshape what happened next. And in doing so, they built something that behaves, at least on paper, as if time inside that little quantum system is running the wrong way. And I guess before we get into what that even means, because reversing time is one of those phrases that sounds like it belongs in a movie trailer, it's worth saying that this is a real result published in a real physics journal, and it's genuinely one of the stranger things to come out of quantum thermodynamics in a while. So let's actually get into what they did, because the reality, as usual, is a lot weirder and a lot more interesting than the headline. But first, a super quick refresher on why time even has a direction in physics, because this is the part that trips a lot of people up. If you watch a video of two billiard balls colliding and then you play that video backward, it still looks basically fine. The balls bounce off each other in a way that doesn't violate any laws of physics. But if you watch a video of an egg cracking on the floor and then play it backward, you immediately know something's wrong because eggs don't uncrack. And the weird thing is, at the level of individual atoms bumping into each other, there's nothing in the underlying equations that forbids the egg from uncracking. The laws of motion work the same going forward or backward in time. What creates the one-way street we actually experience is entropy. This idea that disorder tends to increase, and an egg has vastly more ways to be scrambled across the floor than it has ways to be a neat, intact egg. So statistically, you basically never see the reverse happen. That's the arrow of time. It's not baked into the fundamental laws. It emerges from probability, from the sheer number of ways things can go wrong compared to the number of ways things can go right. And here's where it gets interesting, because quantum mechanics adds a twist that classical physics doesn't really have. When you measure a classical object, like glancing at that pot of water, you're not really disturbing it in any meaningful way. But when you measure a quantum system, the act of measuring actually changes it. This isn't some philosophical quirk. It's baked into the math of quantum theory. Every time you check on a qubit, you nudge it, and that nudging is random in the sense that you can't fully predict which way it'll go. And it's specifically this repeated nudging, this back and forth of measurement and disturbance that gives rise to an arrow of time inside a quantum system in the first place. So if the arrow of time comes from measurement, then the obvious next question, and I guess this is the question that Luis Pedro García-Pintos and his colleagues at Los Alamos actually went and asked, is whether you could control that process carefully enough to point the arrow the other way. So this is where the actual study comes in. The paper is called Reshaping the Quantum Arrow of Time. It was published in Physical Review X back in February of 2026, and it's the work of Garcia-Pintos along with Yikai Liu and Alexei Gorshkov, who are affiliated with NIST and the Joint Quantum Institute at the University of Maryland. And what they built is basically a very carefully engineered feedback loop. They designed what's called a control Hamiltonian, which is really just a fancy term for a sequence of electromagnetic fields and pulses applied to the qubit. And this control Hamiltonian is built to mimic the disturbance that a measurement would normally cause. Then, by wiring that control Hamiltonian into a feedback loop, one that reacts to the actual measurement outcomes as they come in, the team could do three different things to the qubit's trajectory. They could cancel out the randomness from measurement almost entirely, which suppresses the arrow of time so the system barely seems to have one. They could exaggerate the disturbance, blurring things further, or And this is the part everyone's been talking about. They could overcompensate for it in just the right way that the resulting sequence of states looks statistically like a movie of the system's evolution playing in reverse. And I want to be careful with the phrasing here because it matters. This isn't the qubit unhappening its own past, and it's not sending information backward through time. What's actually going on is that the team can steer the statistics of how the system evolves so that the trajectories it produces are the kind of trajectories you'd expect to see if you took an ordinary forward evolving process and ran the tape backward. In other words, they're not breaking physics, they're exploiting the fact that the underlying laws don't actually care which direction time flows, and using measurement and feedback as the tool that lets them pick which direction shows up. Now, as a demonstration of just how much control this gives them over the flow of energy, the team also built something they call a measurement engine. And this is the part that got all the harvested energy headlines. Because every time you measure a quantum system, you're nudging it. And that nudge, remember, takes a little bit of energy to produce. Normally, that energy just leaks away into the environment as noise, kind of like the way friction turns kinetic energy into a bit of waste heat. But the Los Alamos team showed that if you're clever enough with your control Hamiltonian and your feedback loop, you can redirect that energy instead of letting it dissipate and pull it back out as usable work. Effectively, the very act of monitoring the system becomes a kind of fuel source. It's a small amount of energy, and I want to be clear that we're talking about the kind of energy that might eventually help power another tiny quantum process or top up a quantum battery. Not anything remotely close to running your kitchen appliances. But conceptually, it's the thing that gets physicists excited because it means quantum measurement, which people used to think of as this passive, almost philosophical act of observing, turns out to be an actual thermodynamic resource. And okay, I guess the obvious question here is, wait, doesn't pulling usable energy out of a system for free break the second law of thermodynamics? And this is where the whole thing connects to something physicists have been arguing about for 160 years, called Maxwell's demon. Back in 1867, the physicist James Clerk Maxwell imagined a tiny hypothetical creature sitting at a door between two chambers of gas, sorting fast molecules from slow ones, and in doing so, seemingly creating order out of disorder without expending any energy, which looked like a direct violation of the second law. It took about a century for physicists to fully resolve the paradox, and the resolution turned out to hinge on information itself. The demon has to know which molecules are fast and which are slow, and remembering that information, or eventually erasing it to reset for the next round, has an unavoidable energy cost, thanks to something called Landauer's principle. So the books balance, after all. The Los Alamos team is essentially building a real, physical, quantum mechanical version of that demon, one that uses the information from its own measurements to do work, and their result lines up with this century-old resolution, rather than overturning it. So where does that leave us? Because there's more than one way to read what this actually means for the future. First, there's the quantum computing angle, since being able to dial the arrow of time up, down, or into reverse inside a monitored qubit could give engineers a genuinely new tool for correcting errors or preparing very specific quantum states that are otherwise hard to reach, almost like being able to unring a bell partway to get the system back to a cleaner starting point. Second, there's the energy angle, this idea of quantum batteries and measurement-powered engines, where instead of quantum measurement being this thing that constantly leaks energy and information out of a system as noise, it becomes something you can harvest from directly, which is a genuinely different way of thinking about the resource. And third, and this is the one that's more philosophically interesting than practically useful right now, is what it says about the arrow of time itself, that it isn't some cosmic law handed down from above, but something that emerges from how we interact with a system, and that under the right conditions, with the right feedback, you can reshape it. But here's where things get a little bit more grounded, because as exciting as the headlines have been, this is, at its core, a theoretical and simulation-based result. The paper itself is upfront that the next phase of the research is to actually demonstrate these Hamiltonian measurement processes experimentally, likely using superconducting qubits, which are a platform well suited to fast feedback and highly efficient detection, and where quantum versions of Maxwell's demon have already been built in other contexts. So nobody has yet walked into a lab, flipped a switch, and watched a physical quantum system visibly run backward on a screen in front of them the way the more breathless coverage might suggest. What exists right now is a rigorous set of control protocols and a mathematical demonstration that the approach works alongside real related experimental work elsewhere, including a 2025 study from a French team that directly measured work extraction from a single qubit engine fueled by quantum measurements, which shows this general territory is experimentally reachable. Just not yet with this exact reversed time protocol running on real hardware. And honestly, that's not a downgrade so much as it is the normal shape of how physics actually moves forward. Someone works out the theory rigorously, shows it's mathematically sound, and only then does the experimental side catch up, sometimes years later, on real superconducting circuits sitting in refrigerators colder than outer space. So the more interesting question isn't really whether scientists have already built a working time machine in miniature, because they haven't, and nobody in this field is claiming they have. The more interesting question is what happens once someone does run this protocol on real hardware and finds out whether reshaping the arrow of time turns out to be as clean in a noisy, imperfect physical qubit as it is in the equations. Because if it holds up, then the strange idea that time's direction is something we impose on a system rather than something the universe hands us stops being a thought experiment and starts being an engineering parameter, something you can dial in like temperature or voltage, and that changes a lot more than just how we build quantum batteries.